In this lesson, we will delve into the characteristics and applications of boring machine fixtures in Project 1, with a particular focus on Task 5.1.1, which covers the specific requirements for boring machine fixtures. We will explore the unique aspects that differentiate boring machine fixtures from other machine tool fixtures, as well as the significance of these specific requirements in actual production. Additionally, through the case study of boring in large aircraft engine compartments, we will appreciate the critical role of boring machine fixtures in high-precision manufacturing. In the field of machine tool processing, boring machine fixtures are a crucial piece of equipment, playing a key role in boring operations. A boring machine is primarily used to bore pre-existing holes in a workpiece using a boring tool. Typically, the primary motion in boring is the rotation of the boring tool, while the feed motion is the movement of either the tool or the workpiece. Boring machine fixtures are mainly used to ensure the correct positioning of the workpiece and to guide the tool during the boring process, thereby ensuring machining accuracy and improving production efficiency. Let's now take a closer look at the specific requirements for boring machine fixtures. Accuracy requirements. The accuracy requirements of boring machine fixtures are among the most critical specific requirements. In boring operations, the dimensional accuracy, shape accuracy, and positional accuracy of the workpiece directly depend on the accuracy of the boring machine fixtures. Taking the boring of large aircraft engine compartments as an example, it requires achieving nanometer-level precision, which poses an extremely high challenge to the accuracy of boring machine fixtures. Dimensional accuracy. The dimensional accuracy of the positioning elements on the fixture directly affects the positioning accuracy of the workpiece. For instance, the dimensional tolerances of positioning pins and blocks must be strictly controlled. Generally, the dimensional tolerances of the positioning elements should be 2 to 3 times smaller than those of the workpiece. Assuming the dimensional tolerance of the workpiece is plus or minus 0.05 millimeters, the dimensional tolerance of the positioning elements may need to be controlled within the range of plus or minus 0.01 to plus or minus 0.02 millimeters. Shape accuracy. The shape accuracy of the positioning elements is also crucial. For example, the flatness error of the positioning plane and the cylindricity error of the positioning hole can affect the positioning accuracy of the workpiece. For high-precision boring operations, the flatness error of the positioning plane may need to be controlled within 0.005 to 0.01 millimeters, and the cylindricity error of the positioning hole may need to be within 0.002 to 0.005 millimeters. Positional accuracy. The positional accuracy between various positioning elements on the fixture, as well as the positional accuracy between the positioning elements and the tool guiding elements, directly affect the machining positional accuracy of the workpiece. For instance, the relative positional accuracy between the center of the boring sleeve and the positioning elements must be maintained within a very small error range. Rigidity requirements. The rigidity of boring machine fixtures has a significant impact on machining accuracy and surface quality. During the boring process, the cutting forces are relatively large. If the fixture lacks sufficient rigidity, it may deform, thereby affecting the machining accuracy of the workpiece. Structural design. The structural design of the fixture must be reasonable to ensure it has sufficient rigidity. For example, using an integral structure or reinforcing ribs can enhance the rigidity of the fixture. For large boring machine fixtures, a box-type structure can be employed to improve overall rigidity. Material selection. Choosing the appropriate materials is also a crucial factor in ensuring the rigidity of the fixture. Generally, the main components of the fixture, such as the fixture body and positioning elements, are often made of cast iron or cast steel. These materials have high strength and rigidity, allowing them to withstand significant cutting forces. Guidance requirements. Boring machine fixtures typically need to be equipped with tool guiding devices to ensure the correct position and movement path of the tool. The accuracy and reliability of the guiding device directly affect the precision of the boring operation. Boring sleeves are commonly used tool guiding elements, and they are divided into fixed boring sleeves and the rotary boring sleeves. Fixed boring sleeves have a simple structure and are suitable for low-speed boring, while rotary boring sleeves are suitable for high-speed boring. When selecting boring sleeves, it is important to determine based on machining requirements and cutting parameters. Accuracy of boring sleeves, the inner diameter dimensional accuracy and cylindricity accuracy of boring sleeves affect the guiding accuracy of the tool. Generally, the inner diameter dimensional tolerance of the boring sleeve should be controlled within the range of plus or minus 0.005 to plus or minus 0.01 millimeters, and the cylindricity error should be controlled within 0.002 to 0.005 millimeters. Chip removal requirements. During the boring process, a large amount of chips is generated. If the chips are not removed in a timely manner, it can affect machining accuracy and surface quality, and may even damage the tools and fixtures. Design of chip removal channels. The fixture should be designed with appropriate chip removal channels to ensure smooth discharge of chips. The size and shape of the chip removal channels should be determined based on the shape and the size of the chips. For instance, for strip-shaped chips, the width of the chip removal channel should be appropriately increased to prevent clogging. Chip removal can be achieved through natural removal or forced removal methods. Natural removal utilizes the gravity of the chips and the flushing action of the cutting fluid to discharge the chips. Forced removal, on the other hand, uses specialized chip removal devices, such as chip conveyors, to expel the chips. Ease of operation requirements. The design of boring machine fixtures should consider ease of operation to enhance production efficiency and reduce labor intensity. Convenience of loading and unloading work pieces. The fixture's positioning and clamping devices should be designed reasonably to make the loading and unloading of work pieces convenient and quick. For example, using quick clamping mechanisms, such as eccentric clamping mechanisms or screw clamping mechanisms, can significantly reduce the time required for loading and unloading workpieces. Ease of adjustment and maintenance. Fixtures may require adjustments and maintenance during use, so their structure should facilitate these processes. For instance, using adjustable positioning and guiding elements allows the fixture to adapt to different machining requirements. Safety requirements. In boring operations, safety is of paramount importance. The design of boring machine fixtures must comply with safety standards to ensure the personal safety of operators. Protective devices. Necessary protective devices, such as guards and barriers, should be installed on the fixture to prevent injury from flying chips and cutting fluids. Clamping reliability. The clamping devices of the fixture must be reliable to prevent the workpiece from loosening during machining, which could lead to safety accidents. Application case. Boring of large aircraft engine nacelles. The boring process of large aircraft engine nacelles is a typical application case with special requirements for boring machine fixtures. The machining accuracy of the engine nacelle directly affects the performance and safety of the engine, thus demanding high precision, rigidity, and guidance from the boring machine fixtures. In the boring of large aircraft engine nacelles, to achieve nanometer level precision, high-precision positioning elements, and guiding devices are used. At the same time, to ensure the rigidity of the fixture, special materials and structural designs are employed. Additionally, advanced chip removal technology and safety protection measures are implemented to ensure the smooth progress of the machining process. Through the case of boring large aircraft engine nacelles, we can see the importance of the special requirements for boring machine fixtures in high-precision manufacturing. These special requirements not only ensure the machining accuracy of the workpiece, but also enhance production efficiency and safety. In this lesson, we focused on the special requirements for boring machine fixtures, including precision requirements, rigidity requirements, guidance requirements, chip removal requirements, ease of operation requirements, and safety requirements. We learned that these special requirements play a crucial role in boring operations, directly affecting the machining accuracy, surface quality, and production efficiency of the workpiece. Through the case of boring large aircraft engine nacelles, we deeply understood the significant importance of these special requirements in high-precision manufacturing. I hope that in your future studies and work, you will fully understand and apply these special requirements to improve the quality and standards of boring operations.